Hey guys, welcome to the Pre-Med Tutor. Today we'll be tackling the Biot-Savart Law. Okay, well, first of all, what is the Biot-Savart Law? Well, it's an equation that helps us calculate the magnetic field created by any current-carrying wire. How do we find that magnetic field? Well, we divide that current-carrying wire into little bits of current, so individual segments that we'll term ds. Each of those segments ds contributes a little bit to the magnetic field, so contributes dB to the overall magnetic field B. Let's look at the rest of this equation. There are a couple of constants, so there's mu naught over 4 pi. There's I, which is the current running through the wire. There's a r squared in the denominator. Now, r represents the distance from that segment of current, ds, to whatever point, let's say point P, that you're interested in finding the magnetic field of. The second part of this equation is actually a cross product, because remember, current has direction. So ds is a vector, and so is r. Now, this r here has the same definition as the r squared in the denominator here, in that, again, it's a vector that leads from your current to your observation point, again, the point where you're interested in finding the magnetic field of. But the difference is that this r is a unit vector, so it has a magnitude of 1. This r does not have a magnitude of 1, and we'll practice later about how to define this and create an expression for r. Now, once we have a bunch of dB values, we eventually want to sum them all up and find the total magnetic field B. How do we do that? Well, we take the integral of all these dBs. That will sum them up and we'll find the net B. To arrive at our working equation, let's substitute our first formula into the second. So pulling out the constants out of from the integral here, that leaves us with only the cross product and the r squared in the integral. This will be our working equation for when we do any calculations with this law. Okay, so let's try to apply this to an actual problem. Here we have two wires, the top one with the current going to the left and the bottom one with the current going to the right, and we want to calculate the net magnetic field, both magnitude and direction, at point P that's located above both wires. Now, at this point, guys, feel free to pause the video for a second if you'd like to try out solving this on your own. If you're still feeling unsure, feel free to follow along for now. Okay, guys. So as a reminder, this is what our Biot-Savart full equation looks like. To clarify certain things about this equation, number one, what ds means. So I already said ds is some little bit of current, right? However, for the purposes of the integral, it's more intuitive and more helpful to imagine ds as dx, dy, anything that fits along with the coordinate system where we want to apply to a problem, right? So let's say we start off with this top wire here and consider this little bit of ds. Do you notice how I can set my own coordinate system? This wire is horizontal, so it makes sense to consider the wire to be along the x-axis. And if I want to start from this rightmost point as my x equals 0, I can then travel along collecting little bits of ds as I go along until I get to the end of that wire. So in this example, I'll be using dx instead of ds for more intuitive reasons to solve my integral. The second point before jumping in and solving is considering what this cross product means. So cross product means that we want to take the magnitudes of ds, which is our first variable, times r, our second variable, and multiply it by the sine of the angle between those two vectors. So I've drawn a sample ds here. This is a sample r vector. My ds has the same direction as my I in this wire, so it's pointing this way. Therefore, this is theta. This is the angle between them. And remember, guys, for any cross product or dot product, the angle theta you want to consider is when those two vectors have their tails touching each other. So their ends are together, as seen in this diagram. That's your theta. Okay, so let's plug in what we just discussed into our Biot-Savart Law equation. So that involves removing ds in favor of dx, as well as realizing that this unit vector r, again, unit vector, magnitude is 1. We can cancel that out and eliminate it. Take note that that r is not the same as this r squared. If it confuses you, feel free to add a subscript or something so that you're not accidentally, canceling out this r with one of these. They're separate things, so just keep that in mind. All right. So the way we calculate the net B at point P is through the superposition principle. That is to say, let's find the total contribution to the magnetic field at P from the top wire, and then add it to the net magnetic field contributed from the bottom wire. So B from the top plus B from the bottom will give us the P at the top. Okay, so let's first concern ourselves with finding the magnitude of the net magnetic field that this top wire contributes to at point P. Okay, this is just the rewritten equation that we discussed on the previous slide. Now, we have our integration variable here, dx. Now we want to get both sine theta as well as r squared in terms of other variables that we know in this problem. So let's first, I feel like it's always best to start with our r and feel comfortable with defining what that term means. So again, looking at this sample r vector that I drew here, however, I could have drawn it from any point. All r means that it starts from where our current is, so wherever our ds is, to the point we're interested in. So if I picked a random point ds here, then my r would look like this, straight up and down. If my ds was here, it would look like this. So the mirror image of the r vector that I just drew. So you can see that this r value, or rather this r vector, while it does change as you move to the left of this wire, there are some things that always stay constant. For instance, this height, which is given to us as the variable d, whatever value that is, this height is always the same. Do you see that? As you move to the left in this wire, the height d never changes. What does change? Well, x, right? We chose to define our coordinate system so that x equals 0 is here, and then this whole length of wire is termed as the variable L. So we're moving from x equals 0 to x equals L. So to account for that, because d doesn't change, x still changes, therefore r is constantly changing, okay? Specifically, we can write r in terms of the Pythagorean theorem. If you notice, this r vector can be split into both a y component here and an x component here. And that's great because we just discussed how the y component for wherever you are along this wire doesn't change, whereas the x one does. So considering that this r vector will always be the hypotenuse of our radius, this r squared is equal to d squared plus x squared. So r squared is equal to d squared, the y value, plus x squared. Again, that's just the Pythagorean theorem. Therefore, that means that r is equal to the square root of d squared plus x squared, just to be explicit about simply what r is. Great. Now let's look at how we can substitute sine theta. Well, it's very similar. You'll realize that there are a lot of trigonometric relationships that you want to realize in these Biot-Savart Law integrals. So specifically sine theta. So let's look at our theta here. Well, theta we can define in terms of a sine relationship. Specifically, d, which is our y component here, d over r is equal to sine theta. Okay, so after our two substitutions, let's now write in our bounds. We already talked about this a little earlier when we talked about setting up our coordinate system, but realize where we're moving from. We're moving from where we considered x equals 0 all the way to the length of the rest of the wire, so L. Remember, any bit of charge contributes, or sorry, any bit of current, excuse me, contributes to a magnetic field, right? So It doesn't matter where the source is, as long as it's there, it'll affect point P. So once we plug in 0 to L, let's do the integral. This is what that integral looks like as a result, and then once you plug in those bounds, this is what you're left with as a final answer. Now, remember, this is only the magnitude of the magnetic field. We're also interested in direction. So this is where the right-hand rule comes in. If we look back at the diagram, this top wire has current running towards the left. So what we do, we point our thumb in the direction of the current. So if you're doing this along with me, your thumb should be pointing to your left. And then the curl of your fingers indicates the direction of the magnetic field. So again, thumb still pointing to the left. If you curl your fingers, you realize that to the top, so above that wire, the magnetic field is pointing into the page, and then below the wire, as you wrap your hand around, the magnetic field is pointing out of the page. Since point P is above the wire, that means that the direction of the magnetic field there is into the page. Okay, so we've done the top wire. Now let's do the bottom wire. The good news is, if you understood how we calculated everything and assigned variables to everything for the top wire, the bottom wire is very, very similar. Really, the only difference is now we have to reevaluate the two variables we substituted for in the beginning. So remember, that was R and that was sine theta. So always reevaluate what your R is. You can't always trust, oh, it's the same thing. Indeed, in this problem, if well, first let's establish our coordinate system. So this bottom wire current is moving to the right. So let's establish our X to be this left-hand side, and then X equals L to be this right-hand side. Okay, so I drew out a little bit of ds here. Remember, R is always moving from that little bit of current to our observation point. So this is an example of our R. Now, our R value is slightly different now because we also have an additional Y component, height H here. So again, same principle, so same using the Pythagorean theorem to establish what R means, but take into account that extra Y component. Our X is still the same. Again, we're just moving along and our X position changes as we move through the wire. Similarly, sine theta, very similar, just account for that extra height in the numerator. Okay, and now this first step here substitutes for sine theta. The second step substitutes for R. This is what you get out of the integral. Notice that our bounds are the same because our coordinate system setup is essentially the same. It's just moving from x equals 0 to x equals L to cover the full length of the wire. And once you plug and chug and do all the math, this is what you get for your B value. Now, again, don't forget, do your direction. So same right-hand rule. This time my current is pointing to the right. So right now your thumb should be pointing to the right. My fingers are showing me how the magnetic field is pointing. So you'll notice as you curl your fingers around to the at the top, so above the bottom wire, the magnetic field is pointing out of the page, and then below the wire, it is pointing into the page. We're interested in point P, which is above the bottom wire. So the direction of the magnetic field, as contributed to by the bottom wire, is out of the page. Okay, so we did our individual parts, right? We found the magnetic field, magnitude and direction of the top, as well as that of the bottom. Now we just have to add them together, and both of them are in either the plus or minus z direction. So that's why we can simply just add together the magnitudes to get the net v. And as you can see here, I show those exact two expressions added together. Now you might think, okay, we worked entirely in variables. Can we say for sure where what's the direction of the net magnetic field? Well, yes, we can, because let's compare these two fractions. They're essentially the same except for certain terms in the denominator. So here you have a d and a d squared. Here you have a d plus h and another d plus h squared. the bigger your numerator, the bigger your denominator is, the smaller your overall value is, which means that this term is smaller than this term. That means that this first term, which is the magnetic field caused by the top wire, is what's going to dominate. So its magnitude is greater than the magnitude of the bottom wire, which means that the direction is going to be slightly favoring the magnetic field created by the first wire, which, as you'll recall, goes in the minus k hat direction, or into the page, into the screen. And that's it, guys. I hope you enjoyed this video. Please leave a like and subscribe to my channel if you'd like to see more videos like this. And as always, feel free to comment if you have suggestions for other STEM topics that you'd like to see videos on. Good luck, guys.